Lab Guy here. This is part 2 of the big NBTV televisor. Today we're going to look at the new illuminator module which I've constructed. I'll go into the details of its construction and we'll look closely at how it's put together. So let's get on with it. Let's start at the beginning. I used a plastic project box for the enclosure. I mounted the tricolor LED. It's a high power tricolor LED RGB onto a piece of my favorite circuit board material. On the back of this LED is a heat sink, which I put some silicone heat sink grease so that it would contact the ground plane of this bit of circuit board. What I didn't know at the time is that the heat sink is common with the anode of the red LED in this particular lamp, and I don't know what brand it is. I bought it surplus online. I think I bought this on eBay. So it's a this is what you get kind of LED. It works very well. The ad said it was for a track light. So it's one of those that you can set to any color of your choice. It works very well. So it's got 6 pins. The 3 LEDs are independent, with the exception of the anode of the red LED is common to the heatsink tab on the back. I put silicone heatsink grease on it to couple the heat into the ground plane of this piece of circuit board. The circuit board is just basically there to support the LED. You'll note there's no additional reflectors or diffusers inside the box. On the back side, I've placed some spacers to hold the active circuitry. I brought out the wires and terminated them in a 4-pin Molex connector, which connects to 4 DuPont pins on the driver circuit board. I mounted 2 right angle brackets for bolting this to the televisor, and all of my hardware is American standard gauge stuff. This is a number 440, number 440 threads to the inch, and for mounting to the box I use what are called hermaphrodite standoffs, which are male on one end and female on the other. If you don't know what I mean by that, ask your mommy and daddy. So I use these a lot. To mount them to plastic or wood, you drill a hole 3/16 of an inch in diameter, and a number 4 screw can be threaded into that as long as you use a compliant material. You might, these are stainless steel, you might force these into an aluminum panel, but I would suggest using a tap. So they stay very well. If you end up having to disassemble and assemble your project multiple times, the holes of course can get reamed out, and in that case they get loose before you're done. Just put a drop of glue in there. The screws on the right angle brackets are also 440s. These are little shorties. I think they are 1/4 inch long, and that's pretty much the mechanical construction of the box. I junked a couple of illuminators that were for flatbed scanners. These illuminators had cold cathode fluorescent lights in them for backlighting negatives and slides. Since I never used those, I picked those illuminators up at flea markets for next to nothing, probably 50 cents or $1. So I scrapped them. They were very long. You know, they were long, and I cut them into multiple short pieces, thirds in this case, and stacked up the layers of diffusers to make this a very powerful diffusing mechanism. And then there was a sheet of clear plastic which I salvaged, and I put one on the face and another on the back to prevent scratching of the white diffuser material. I used black gaffer's tape to mask the rim of the disc to cover up the sink holes so that the illuminator does not shine through them. When this is installed, it in the box, it is pretty much centered up with the LED behind. The diffusion, without the tape, you could see that there is a pretty strong hot spot, but it is very even in the center, larger than the imaging area of the NIPCOW disc. So this diffuser works just fine. So let's place that on the box and bolt it down. Always start all your screws before tightening down the first one. Otherwise, you have to come back and loosen them all again. So there we go. And that closes up the illuminator box completely. And now let's move on and look at the electronics. Let me put up the schematic. All right, and here is the execution of that schematic on this board that you're looking at. It has the 3 power transistors, the heat coupling aluminum, and a couple of very nice finned heat sinks, because the transistors are dropping about 9 volts at 150 milliamps a piece, so they do dissipate a few watts. They get pretty hot. 3 resistors here. Not the pots. The 3 resistors are 3 ohms each. I will be changing these to 2 ohm resistors so that I can get a higher current. These are the emitter resistors that you saw on the schematic. These are the input pots. They're 5K each. And on the input connector, I have 75 ohm terminating resistors because my RGB video source is a 75 ohm source. These are 5K pots. If you were driving this from audio sources like the output of a sound card, you would leave off the 75 ohm resistors. The quad op amp is down here. It's an LM324 general purpose op amp, and the board is hand wired on the back in my usual way. I used red wires for the red signals, green wires for the green signals, and blue wires for the blue signals. The orange wire is the plus 12 volts that powers the unit. And there are no black ground wires because ground is provided by the ground plane on top. That is the entire driver board right there. Very simple, very straightforward. This is a voltage to current converter directly. 1 volt in at the moment gives about 133 milliamps per channel, and there's 3 channels: red, green, and blue. So that's the driver. Let's install the driver now onto the diffuser box. Alrighty, this way is up. Again, it's all held together with number 4 hardware. Let me start the first screw. There we go. You'll note that everything I build, I use connectors so that the units can be disassembled, because the way I build things, you have to put them together and take them apart many times before you've iterated into a working design. I use empirical design methodology, and it is how I design. And so there's a lot of put it together, take it apart. The board is now installed onto the box. The LED wires come through, red, green, and blue for the cathodes, and the orange wire is providing 12 volts to all 3 anodes. And that is the entire illuminator right there. I use old circuit boards in the way that a carpenter uses plywood. I refer to this stuff as nerdwood. This is a nerdwood panel. You can drill it very easily, you can file it, you can shave it with your X-Acto knife. Very versatile stuff, and you can get it by the ton out of dumpsters. In the way that this unit is put together, here's the disc. This board sticks out to support the illuminator. So the first thing we're going to do is attach the illuminator to the support board. Oh, if old lab guy could see, huh? There we go. That's one. Oh, it's there somewhere. Two screws holding on the illuminator box with the heat sink above, circuitry on the back, diffuser on the front, ready to go. I use number 632 screws, American gauge again, because I'm in America, no other reason. And okay, there we go. That one's started. Well, the board won't fall now. That one goes on. And we tighten them up. Alrighty then. And here you can see the clearance between the disc and the illuminator. The cable for connecting the illuminator is a 6-pin Molex connector that connects like this. The pinout on this 6 pins is red ground, green ground, blue ground. Very straightforward. Everything I wire, I try to make it as logical and simple as possible. At this time, I don't have the servo working for this unit, so I'm driving the motor directly from a variable power supply, and it turns out that the correct voltage for this DC motor is between 4.6 and 4.7 volts. To get it to run at the right speed, the illuminator is driven on 12 volts DC and draws about 350 milliamps. The motor runs on 4.65 volts and draws 600 milliamps. We'll hook it up, and as you saw in the intro, we'll turn it on and hope that it still works. Hope that you can see it. Let me lower you down. You get a better view. There we go. All right. And nothing. Okay. Oh. The Aurora converter turns itself off. Well, let's hope I have the right test pattern. I do. And there you go. It's rolling because there is no servo circuit. But as you can see, we can see the color bar test pattern that is automatically generated by the Aurora converter. Unfortunately, the WC1 World Converter by Aurora is no longer available, so you'll have to watch closely for estate sales, because these are owned by antique television collectors. If you can find one, you're going to pay for it. I bought mine while it was still in production, and it cost $1,050 at that time. Now this is the completely adaptable deluxe model. There are some that only put out one format or a few formats, like mechanical TV, and others will do electronic TV, but in a more limited range. So there you go. The illuminator box is working. Let me turn off the main light, and you can see that we are now producing a good flat white light source for the mechanical TV. So that is the current state of the big NBTV televisor. So once again, I hope you've enjoyed this video. If you did, you know the spiel. And if you know somebody who likes these kinds of things, tell them so they'll come and subscribe. And until next time, Lab Guy out.